Okay, so when covering chapters 5 and 6, um, we covered a few things. Let's go over what we covered there. Reminder that chapters 5 and 6 um, are going to take up about 11 questions of the 40, second biggest category, and it's the last test that you've taken at this point in time. Okay, so we start off chapter 5, which is on electron configurations. We started off learning about light as a tool. And the reason we're going to use light as a tool is because we won't need to kind of dig into what's going on with the electrons in an atom. So we have to dig into the atom. We have to understand light a little bit because we're using that to kind of get an idea what's going on in the atom. We learned about the electromagnetic spectrum because we're going to be using parts of it, including the visible light spectrum, know the colors of the rainbow, Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet, and know that that's part of the electromagnetic spectrum. Know the other parts of the electromagnetic spectrum, especially those that are right next to the visible spectrum, which includes infrared and ultraviolet radiation, but all the other ones too, because that's what we're going to use to get some information from the atom. Know that any type of electromagnetic radiation has a specific amount of energy, which is correlated to wavelength and frequency. And there are equations that related energy to frequency. E is equal to h times frequency. Remember, h is Planck's constant, a good thing to put on your cheat sheet for the final. And wavelength and frequency are related to each other inversely. The speed of light is equal to the wavelengths times the frequency of a photon. So know that equation too. Remember that the speed of light is also constant, 3 times 10 to the eighth meters per second. Okay. So once we know all that, we can go ahead and dig into the atom. And that's what Niels Bohr did in his Bohr model of the atom. He came up with, using the Bohr equation right here that I have right here, he came up with the idea that electrons are in energy levels in a atom. Okay, and how did he come up with that? The atomic spectra that is given off by every element. Every element has its own unique atomic spectra, and it gives off specific wavelengths of light. And where do those specific wavelengths of light come from? Well, they come from transitions between energy levels by the electron. When the electron falls from a specific energy level to another energy level, it gives off a specific amount of energy. That energy has a specific frequency, and that specific frequency has a specific wavelength. And we can detect those and figure out what the difference is in energy between the energy levels. Okay, so Bohr came up with that idea. It worked for hydrogen, but it didn't work for anything else because apparently it wasn't sophisticated enough. It wasn't complicated enough. So we need to get a little more complicated. The math gets too crazy. So we just started talking about orbitals. When you do the math, this is what you get out of it. You get these shapes around the nucleus where an electron can be found. So we learned about orbitals, and orbitals are found in sublevels. So not only are there energy levels, there are sublevels. There are levels. Uh, each energy level is broken up into its own levels, so sublevels, and those sublevels are made up of different orbitals. There's an S sublevel, a P sublevel, a D sublevel, and an F sublevel um, when they occur. S sublevels are found in all energy levels. P sublevels are found in all energy levels starting with a second energy level. D sublevels are found starting with a third energy level, and F sublevels are found starting with the fourth energy level. That's where the electrons go. So then we started writing electron configurations, and we wrote them in sublevel notation or orbital notation. That's that whole 1s2, 2s2, 2p6, 3s2, 3p6, all that stuff. And you can write the whole thing. You can do a shorthand using a kernel. Remember, the kernels are when we go ahead and use um, we use noble gas electron configurations to kind of shorten how long our electron configurations are. We just go ahead and say, all right, this part is just the previous this noble gas, and then we just add on to it. We talked about exceptions to electron configurations, when you can half fill a sublevel. When things are supposed to be D4, they'll become D5 because you'll promote an electron from an S sublevel. Or when they're supposed to be D9, you'll end up with D10 because same thing, promote an electron from an S sublevel. Because having a half filled sublevel or a completely filled sublevel apparently is a really good thing. And from your electron configurations, you should be able to calculate the number of valence electrons uh, that an element has. Okay. And so, yeah, be able to come up with these electron configurations for the elements. Once we learned that, we went ahead and read about the periodic table in chapter 6. And you should know that it's organized in order of increasing atomic number. If you go row by row, left to right on each row, each this each next element is just one bigger in the atomic number than the previous one. It was developed by people like Dmitry Mendeleev, reorganized by people like Henry Moseley. Periods are the rows, groups and families are the columns. The columns will allow you to figure out how many valence electrons an atom have, uh, and atoms of specific elements have, um, because they're all kind of put together based on their properties, and their properties are because of valence electrons. So you should know that basically the number of valence electrons an atom has is the one digits of the column number when you are talking about the main group elements, columns 1, 2, and 13 through 18. If you just look at the column number at the top, take the ones digit, that tells you how many valence electrons all the elements in the column have. You can separate the periodic table into metals and nonmetals, and as we're finding now in chapter 8, that comes in handy because that'll tell us when we have a ionic compound versus a molecular compound, if you know whether you've got a metal and a nonmetal in your formula. You can look at the periodic table and try to basically get a read of the electron configuration of an element just by where it's at on the periodic table. The periodic table can be broken up into the S block, the P block, the D block, and the F block. And based on where it is in the periodic table is how the electron configuration ends for that element. It can even give you the order of filling of the sublevels by just kind of seeing how the periodic table is, filled in. And then we talked about periodic trends. Just by using the periodic table, you can get a trend as to what you expect the sizes of atoms to be relative to each other. Um, and like, for example, the atomic radius, as you go left to right on the periodic table, uh, decreases. Atoms get smaller due to larger effective nuclear charge when you go left to right across a period or a row. And when you go down a column, they get bigger because you're adding more energy levels, and those outermost electrons are getting further and further away from the nucleus. Ionization energy and electronegativity are the opposite trend. They get larger as you move left to right in the periodic table, and they get smaller as you move down on the periodic table. You should know what ionization energy is and electronegativity also. It just has a definition, and know their trend.